How are you guys doing?
Hi, Olga.
Good, good.
Hey.
Hello. Hi. Good to see
Morning.
you.
Likewise.
It's very early for you.
Yeah.
I'm sorry. We're sorry for that.
How are you doing? How is your son?
Yeah, good, good. He's on the way to daycare, so very good. Thank you.
Okay, so while people are getting in, let's start the webinar. So today we have Professor Hao Zhu giving a presentation in the DIGA webinar series. So it's a pleasure to welcome Hao to this DIGA series. So Hao is an associate professor at University of Texas at Austin. She's the professor at electrical and computer engineering, and also a TAE Research Foundation Centennial Fellow at that university. She got the MSc and PhD degrees from the University of Minnesota. That was in 2009 and 2012. And then from 2012 to 2017, she was also a postdoctoral research associate, and then also assistant professor at the University of Illinois at Urbana-Champaign. Her research focus in terms of theory is on developing algorithmic solutions in general for machine learning and optimization. I also had the pleasure to collaborate with her on some sparse reconstruction problems, so that was really a joy to work with her. In terms of applications, she focuses a lot on, currently at least, on future energy systems, modeling and controlling the smart grid, and also the talk today is about that. So we're really looking forward to that. She's also a recipient of the NSF Career Award and faculty advisor of 3 Best Student Paper awards at the North American Power Symposium. And she's also then associate editor for the transactions on smart grid and transactions on signal processing. So it's a pleasure to have you here, Hao. So go ahead.
Yeah, thank you very much, Dr. Lius, for the introduction. So my name is Hao. I work mainly on power systems for the last 10 years or so. So it's great to present some of the work in connection with power system, learning in power systems to graph neural networks in this talk. Let's move forward. So so recent years, we have also seen the increasing interest of using machine learning and AI for better operating the energy systems, as in many other domains. So here are some potential applications people were interested about. So this increasing interest is thanks to the new data sources that we have available in power systems, including what's called single phasor data, or smart meter data, and weather data, and some geographic data. So there's still a strong focus on how we can use machine learning more effectively, because in energy systems, especially in real-time power system decision makings, there are a lot of domain-specific challenges in terms of like physics modeling, or in terms of the type of problems that we have. So there's still a way that we need to bridge the operations and problems at hand with the type of machine learning tools that we can use. So with that as the context, I would like to say that there is an interest of using the physics grade property, which is it is a graph itself, to better design machine learning tools for this type of real-time power system operations problem. So specifically, if we look at, say, high voltage transmission systems, and these are like voltage above like 100 kilowatts or on and above 100 kilowatts-ish, usually these are very large graphs themselves, like ranging from 1,000 to tens of thousand nodes. And here are two illustrations. So one is the interconnection for the Texas grid. It's a synthetic model, meaning that it's not a real system, but generated to look like the real system for research purpose. And another one is a Polish grid. So I think, maybe an example from the European side of the system. It's also like both of them have 2,000 nodes-ish. And these systems are also like meshed topology. So we have a reliability. If one line fails, there's still a backup line. And these graphs are not very dense. So the average nodal degree is around 2 to 3. Which means that the number of edges are also on the same order as the number of nodes. So there are a lot of interest in exploring the structural properties of the real-world power grid as showcased in these two papers, which have identified a lot of these kind of properties from a range of different real-world systems. So while my talk is focused on these high voltage transmission systems, in the residential side, it's also have a lot of analysis as well. The major difference in the residential distribution grid is that it's mainly a tree topology for most of the systems because we don't have a lot of capability to build lines. So the topology of the grid or the graph representation of the grid also would come in when we look at an important physical property of the grid, which is called the power flow model. Basically relate how the power quantities with the system states. So if we view the power network as the graph representation show here with the set of the nodes and the set of edges, specifically on the node side, which we call the bus, there are two important properties or quantities. One is the complex voltage phasor, which is the voltage magnitude VI and the phase angle theta I as a complex value. And this is considered as the state of the grid. If we know it everywhere in the system, then we know the system states. And the other quantity specified at every node is the complex power injection, which is also a complex value, separated into the real part PI and imaginary part QI. And the relation between them is called the power flow, and it's nonlinear, which is usually a special condition when we think about how to formulate optimization control problems for power systems. And the relation between the two, if we connect the complex power injection through all the nodes into a vector, and similarly through all the voltage phases through all the nodes into a vector, they're related quadratically because the power is the product between voltage and current is related to the voltage under this so-called Y-bus matrix, which is essentially graph Laplacian. So it's based on the connectivity and also the line parameter of this underlying graph. So it is basically a weighted graph Laplacian. So this property indicates why the physics grade side, there is a graph connectivity or topology related property based on this nonlinear power flow model. So there are also interests to linearize the power flow. And then this is essentially a linearized version that you can think of. There's a linear relation between P and the state theta. And then from the theta, you can generate all the line flows. So this relation between the injection P to the line flows based on this matrix S, which is also called injection shift matrix, like a sensitivity factor here, is also based on the graph Laplacian. So here's a very quick overview, but essentially when we know the states, and then we don't know the states, and we observe these power, then this is the very classical problem called state estimation. And if we want to control the states, then we can also manipulate or set up these power injections. And this is what's another classical problem called optimal power flow. So these are like the type of problems that we can do to based on the underlying nonlinear power flow in the physical grade. So with that connection to the graph connectivity and also topology, there's a high interest to use graph learning in power systems. So I know a lot of people, especially the host here, have a lot of pioneer work in graph signal processing or graph neural networks in recent years. What I'm highlighting here are more of the applications into power systems. For example, using GSP to set up the nodal voltage phasor that I mentioned earlier as the graph signals, and then using GSP techniques to do some dynamic analytics in this work, and using GSP techniques to deal with the low observability issues in state estimation, while these voltage phasors are unknowns. And when using GNN, the application domain of problems are more general. So they are using them for typical anomaly detection and localization, and also state estimation by some of the audience here, and optimal power flow problem, which I will talk more today, and a related problem called optimal load shedding, which is very similar, but working more on the emergency situations. And the other type of problems is to deal using GNN to deal with renewable data by looking at their underlying spatial colorations as well. So we have a work on that, but I'm not gonna focus on that today. So with that, my talk today will look into using this type of graph learning, or like specifically the information on the grid topology and this grid-based dependency to design grid operational task. And then the first one that I'm looking at is the topology-aware learning for optimal power flow, how we use the topology information to use the GNN technique to simplify the model structure. And we find that it's very useful for also adaptivity, meaning that when the topology changes, the GNN-based OPF learning technique can better adapt to the new topology. And the second one is not specifically GNN, but very related, is when there is emergency happened in terms of line failures, then how we can use the learning techniques to better understand what is the best emergency response policy under these situations. Specifically, what we advocate is a scalable neural networks that you use only like local information, so it eliminates the need of network-wide communications to more promptly react to the emergency situation. So without further ado, the first problem is on machine learning for optimal power flow. So as I mentioned, this is a very classical problem in power systems. Traditionally, if you think about that, we have the input, which are basically the load demand everywhere, and also other related information. We know that we can use a powerful solver, optimization solver, usually gradient-based, to find the solution. So the idea here is that if I have all of these input-output pairs from historic data or from synthetic data for multiple instances, then I can train a neural network offline and then directly give me the input-output relation for this optimization problem. So after appending this pre-trained input-output model in online solution, it's going to be much more accelerated. So there's a computational benefit to do that, in addition to other potential benefits. So there have been a lot of interest in this problem using machine learning for this OPF, especially due to the variability of renewable resources, and then the real-time neural network-based OPF solver can be very fast for prediction, so it can accelerate the solution, obtaining the solution process. So people have thought about using that to also warm start the original AC non-convex AC OPF problem. And then a lot of interest to look at the feasibility issue to deal with the line flow limit violation. Sorry, this is supposed to be, there's missing an O here. And then using regularization to deal with feasibility based on the KKT conditions. And then also works to connect it to like the actual convex OPF, which we can solve easily, and then look at the duality analysis to that. So I want to point out that a lot of these papers are using fully connected neural networks that are not based on the topology. So the its ability to adapt to when the topology changes is unclear. For a complete review, Professor Minhua Chen at CU Hong Kong has put up a list of papers on machine learning for OPF on this wiki page. This is very useful. So to deal with the topology adaptivity issues, what we want to do is to explore the idea of using graph learning approach. So we can first reduce the model complexity of these neural networks and also try to adapt to new topology. Notice that this topology adaptivity is very important in real-time operations because there could be emergencies like weather events caused like the line failures. So there is a need that, okay, these neural networks should adapt to the actual topology of the grid if there is any emergency events happening. So this is what we are trying to use GNN to be more adaptive for. So go back to the formulation of real-time, the non-convex AC OPF under the non-linear power flow model. The goal here is to determine to manage this complex power injection, the PQ variable here, and then the voltage phasor is the associated variable because they are related based on this non-linear power flow that I mentioned earlier. So we want to design PQ to under a list of constraints. There are upper lower limits for them. There are also upper lower limits for the voltage magnitude. In addition, we want to work on achieve some economic benefits. So this objective here relates to the cost of providing a certain level of real power generation output from the generators. So these are usually convex cost, piecewise linear, and also commonly as quadratic cost. Most importantly, in this problem, which is essentially a resource allocation problem, in addition to these nodal quantities, the constraint that we're looking at is the line flow. So this Sij denotes the apparent line flow on each edge. And then they should also be within a certain limits. So this is one of the most important constraints. And then this is what we usually discuss about the feasibility issue as shown later on. So with this setup, essentially as a resource allocation problem, we can think about that, oh, the input information we need is this nodal upper lower limits and also the local generation cost captured by this vector Ci. So if it is quadratic generation cost, then we need to know the quadratic and linear coefficient into this nodal input information. On the output, which is our decision variable here, is we want to know the PQ injection. So there is a natural way of using GNN to do it. However, if we set up this way, we know that the number of parameters in each fully connected neural network layer, then it's gonna scale quadratically. with the number of nodes because of the scaling on both the input and output side. So can we explore graph connectivity or topology to do it? Definitely we could. So there is a group of UPenn researcher who has used graph GNN to do this OPF prediction problem. However, there is one issue in that. So we know from GNN output, we're expecting some kind of topology dependency or locality, meaning that if the two nodes are very close to each other, we expect their generator output to be similar if we use that to use it to predict the PQ injection. This is not the case because the generation output depends on the economic model. If one node has a very costly generator and then the other node's generator is very cheap, then their generation output does not scale because of their they are very close to each other. So we became interested to identify the OPF outputs that are dependent on location. And then we found two of them. One is called locational marginal price, and then the other one is the voltage magnitude as a OPF output. So first on the locational marginal price, it's essentially the due variable or the Lagrangian multiplier for the OPF problem. So here is a simplified version as the DC OPF, the linearized OPF. If we consider the power balance and then the P injection limit and also the line flow constraint, which I mentioned is a very important feasibility constraint. So if we introduce Lagrangian multipliers, lambda for the power balance and mu for the line flow limits, then this LMP, denoted by the pi here, are essentially based on the optimal due variable lambda and mu here, according to this S matrix, which I mentioned is the linearized power flow matrix, the sensitivity factors. And if essentially pi here, or the LMP, is what we meant the sensitivity of the objective with respect to P. So if at one location the pi is higher, then meaning that if you change that location's power injection by a small value, then the cost will gonna increase by proportional to this pi value. So this is what the connection to the Lagrangian, the duality analysis for these problems. So although this analysis is based on the linearized or the convex OPF, this same intuition also holds for the nonlinear and the AC OPF. So this is the sensitivity of the objective to the P here, to the injection P here. Interestingly, based on this relation here, the pi only depends on the congested lines, meaning that when the mu here, or this line flow limits becomes active, accordingly, this multipliers mu will be non-zero, and then it means that there is active constraint here, then these corresponding multipliers are non-zero, and then the pi is related to the non-zero mu's through this S matrix, which I mentioned only is based on the graph Laplacian. Actually, the B here is the weighted graph Laplacian in the linear case, and A here is the adjacency matrix. So you can think of why, this is the reason why the LMP pi here depends on the graph topology, or has this topology dependency. So on the other output, the voltage magnitude, it also has a dependency because it's heavily dependent on the reactive power or the Q differences. So it also is spanned by this Laplacian inverse matrix. So by the way, these Laplacians are reduced ones, so that's why they can be inverted without the rank deficiency issue. So what I want to highlight here is that these two, as the output of OPF, is spanned from the eigenspace of the graph Laplacian, and that's why they have this topology dependency or strong topology dependency, making them ideal for GNN-based prediction. So here are some real-world OPF LMP map where you can see the topology dependency, where usually like when you see these high prices or these darker colors, they're because there are congestions in this area, so that the electricity price here are more expensive here than the other area. And similarly here, which is in the California area, you can see that in the population center or in Bay Area, the price are more expensive than the rest of California. So, but then what is showcasing here is definitely the price, the LMP depends on the connectivity, or the here is the geographic distance as showcasing on this map. So we're going to use GNN for predicting the OPF. And then to set up the problem, then we mentioned about the nodal input. They can be collected in this matrix X0, which is the number of nodes by the number of futures per node. And then in each L layer of the GNN, we have two Lindenberg parameters. One is the topology-based graph filter WL here. So I know in some contexts, the graph filter can be pre-designed. So we set it up as a graph filter, but it's a trainable parameter, but it's based on the topology, meaning that the entries are fixed at 0 if the two nodes are not connected. And then for the connected lines, then the parameter can be tuned up and down based on their inference strengths. And then there's also a future parameter which can map the future dimension to a higher dimension for nonlinear mapping to explore the nonlinear relation between the OPF input and output. So clearly with that GNN architecture here, the number of parameters specifically with this W matrix, the graph filter here, scales with the number of edges. And then because we know average nodal degree in power network is 2 to 3, so the number of edges also scales with the number of nodes. And then the number of parameters here has a linear scaling with the number of nodes and here compared to the fully connected quadratic scaling. So after doing that, we should connect these two output LMP, the price, and then the voltage to general OPF variables. The first thing we want to do is to map it to the nodal injection, the PI here. And we know that this is based on the fact that LMP is the sensitivity of the objective with respect to PI. So we can use this economic model to set up what's going to be the optimal PI based on the LMP prediction. And then if the generation cost is quadratic, then this becomes a linear transformation with a projection to the upper lower limits of PI. So it's a very simple operation or projection layer from the LMP to the nodal injection. After that, we can also approximate the phase angle. So this is the angle of the complex phasor, and then using this linear model. And then after that, this becomes a fully completed layer to go from the GNN output, which is the pi and then the voltage magnitude, to convert it to the states, which are the phase angle and voltage magnitude, and then be able to generate all the power flow, including the line flow limit, the line flow apparent power on the lines. So this completes the way to generate all the physical quantities for the power flow. So the benefit of doing that is we can easily set up the feasibility regularization. So if we look at the pi and v prediction, then these are the loss function can be the mean square error between the prediction error on this, or we can use other norms for different benefits as well. But then interestingly, after setting up the generating all the power flow variables, we can further set up the feasibility regularization, meaning that this line flow limit can be, violation can be mitigated or reduced by looking at this term. And this predicted line flow is purely based on the prediction variable pi and v, and that allows us to very easily set up this feasibility regularization. And as stated here, this is a fully feed-forward neural network and then can be efficiently trained through autograd or backpropagation. So here are some results which we showcase the prediction arrow in a different size of system. One is a 118 node system and the other one is a 1300-ish node systems. So we look at the prediction arrow in the price and then the voltage magnitude and then the generation, the power injection and also the feasibility violation and also the number of parameters in the model. So clearly the left one are the orange magenta ones are the GNN ones, and then the blue ones are the fully connected ones. The number between the two, the number of parameters reduction is huge. And interestingly, we found out that they still maintain or even improve the prediction performance from the fully connected model. Actually, in this smaller case, for the price prediction is slightly better. And then similarly for the voltage prediction, actually the accuracy is much better than the price prediction for voltage in this case. The voltage prediction, the performance is also very comparable. And then similarly for the injection prediction, the performance is very good as well. And most interestingly, if we look at the feasibility violation, this is the violation of the physical line flow limit constraint, as in the optimization constraint there, we see that using the feasibility regularization, there is also additional benefit going from the GNN to the feasibility regularized version. So the improvement over of GNN over the fully connected neural network, and also the improvement of using feasibility regularization has been demonstrated here. Similar results can be shown at the DC OPF, which we didn't need to do that. We just did it for fun for the linear DC OPF prediction. And very interestingly, for the larger case, the feasibility violation is very small. Well, you can see that the prediction value, the arrows are similar, but then the feasibility violation is very small. So in this kind of problems, because of the complex feasibility region, even though we have the similar arrow in predicting the physical quantities or decision variables, but just changing them slightly, the limit, the constraint violation can be reduced significantly. So we also use that for the line congestion prediction. So I mentioned that this locational price difference is coming from the congested lines or this active line limit constraints. So we can also just do predicting these whether these lines are congested or not, and then this can be simply done by using a fully connected layer as the last layer. And then since it's a classification task, we can use cross entropy loss, so that we still can use GNN layers in the first few layers or the fully connected one. So by comparing the two, the active line congestion prediction performance are very close. So GNN is very compatible, but then there's a slight improvement because I guess the model complexity has been reduced significantly. So the final part on using the GNN, which is getting to what we wanted as a strong motivation of using GNN, is this topology adaptivity. So during real-time operation, so we don't know a day ahead that there could be some weather event, a lightning event, or there's some line can fail. So in real time, when these events happened, then the pre-trained neural network model needs to be able to adapt to this topology very quickly. So if we design fully connected neural network, there is no strong way to how to do this transfer learning task. So we need to regenerate the samples for this new topology and then do training based on this regenerated samples, and this can be time consuming. So one thing we want to advocate is actually there's some kind of stability in this problem. I think the graph stability properties of graph neural networks has been looked at in this popular work, but then the issue we are looking at here is different. In this work is how the layers of graph neural net can be stable under certain entry perturbations. But here we want to know how these entry perturbation could affect the graph subspace itself, meaning the eigenspace of this graph Laplacians. So one thing we observe numerically is that even under this topology perturbation, then the distribution of the LMP is still pretty stable. So this is the histogram of the LMP under different under the nominal topology and also a perturbed new topology, where you see the distribution of them are still pretty similar for both the small system and larger system here. So one thing we postulate there is that even when there are these B matrix is changed because of the line contingency, its subspace or this span of eigenspace are still pretty similar. So that enables the similarity in the or stability of the LMP output. So we look into that. Actually, for the case of a single line outage, this perturbation of the B, the graph Laplacian, and also its inverse are both rank 1. So this is based on using matrix inversion lemma. We can find this rank 1 perturbation to be inverse. So by defining a metric to quantify the difference between the original subspace or the eigenspace of B matrix and also the new subspace which essentially the eigenspace of the the new B inverse matrix, we can set up this bounded analysis for the subspace difference. Notice that this metric is based on the pairwise eigenvector distance based on the angle difference between the two corresponding eigenvectors. And then the bounded result states that if we know the eigenvalues between the two graph Laplacian inverse has this separation property, meaning that there is a group of large eigenvalues and a group of small eigenvalues. So there is a bond between the minimal separation between these eigenvalues for both the pre-perturbation or the pre-outage B inverse and also the post-outage B prime inverse. So if their eigenvalues can be separated into two groups, actually we can bound the leading subspace, meaning the subspace corresponding to the largest eigenvalues, by looking into this rank 1 based on this rank 1 perturbation bounds. There is also another bound which we further look into how much these perturbations are. So depending on these two bounds, as long as the eigenvalues can be separated by this delta threshold. So the more separated they are, then the better the bounds are. So we can find out that these eigenspace are very similar, even if the graph Laplacian entries are slightly perturbed. So this is the main results we have on this graph Laplacian perturbation, which I think is kind of interesting, slightly different from the typical stability analysis. So we look at the transfer capability of the GNN-based prediction. So we consider a random line outage of 2 to 4 line outage, and these are the high capacity lines. So we pre-train the GNN for the original system, and then we can use them immediately for the new system or we do the retraining using this warm stat with only half of the samples here. So here you show the results, the performance, the arrow performance of the price prediction for both use them immediately for the new topology or do some minimal retraining. Actually, the retraining takes it's very fast. It only takes 3 to 5 epoch. They can converge to this new topology very quickly. We see that interestingly, even without doing retraining, especially for the small system, in a lot of cases, the prediction of the original GNN for the original topology is still pretty good. But of course, after retraining for these cases that are not as good or the performance are slightly worse, the retraining can help to bring down the performance to the original arrow accuracy. So this is very interesting on the adaptivity or the transfer capability of the GNNs. And I think we were saying that, okay, because of the stability of the graph subspace, this is possible. So we don't need too much effort to identify what should be the kind of subspace or the models for the new topology, because this subspace perturbation is bounded. So here are some more results where we see that this bounded perturbation, this distance metric is verified numerically. So the perturbation between the subspace is very small. And also we numerically see that even the perturbation, all the changes on the future filter H is very small as well, because the future filter shows some similarity to the original topology. So these results corroborate that there is a strong capability to adapt to the new topology for the GNN-based OPF learning problem. So this concludes the first part. I know I don't have a lot of more time left, so I'm going to quickly go over for this emergency response problem that we're looking at. It's a very similar problem from the ACOPF, but then the biggest part is that it's working on the emergency situation, which I find is interesting because we're witnessing a lot of more like natural disasters or also sometimes the man-made crisis, which challenges the resiliency of the grid. So in Texas, we have the winter storm, which we did. When I moved to Texas, I never expected that we will have the weather in Minnesota as well. So obviously, people here do not know how to deal with weather like in Minnesota. Yeah, but anyway, so in these kind of situations, it's when the emergency happens, we have to take more drastic measures like reduce the load. So it's not just to manage the generation output. We have to also invoke the load reduction to be able to quickly restore power balance. So there are some other strategies like have backup resources or mobile resources and deploy them for also this more emergency situation. So this problem, if we consider the optimal load shedding, which is to manage the load resources, it's also needs to be done very fast. And then that's why people have been using this machine learning. People have thought about using machine learning for this fast prediction as well. But then all this work look at a centralized problem. So what does that mean? So this problem is a special case of ACOPF. So you can think of that, okay, it is not just to understand what has been the demand at every location. We also want to know that when the emergency happens, does it cause certain failures of the grid components like line failures? So all of this network-wide information needs to be communicated to the control center. And then the control center run an optimization problem to know, oh, for this load, you need to reduce by this amount and send it back to the load centers. So this network-wide information exchange can be affected by communication infrastructure, by latency or certain link failures, which can be quite common if there are already some weather, extreme weather events there. So what we want to address is that, okay, so we can use machine learning tool to replace this centralized optimization. So definitely people have done that with GNN-based learning modules to adapt it to solve this centralized problem. But particularly, can we train these machine learning models so they're more scalable, and also they can be implemented in a decentralized fashion? So definitely this can be the case. So maybe I don't have the time to get to the technical details. So this problem formulation is very similar to the ACOPF. It's just that additionally, we can also set up flexible load demand. And then this changing the load is much higher cost than changing the generation. So we are incentivized to first use the generation resource. And then when it is insufficient, then we are going to change, we are going to invoke the load resource to quickly restore power balance. So based on, because the similarity to the OPF problem, then definitely the LMPs or the dual multipliers can, which is the sensitivity, can be used to fully determine the nodal input. So we're going to explore the similar idea here to predict this LMP or the dual variable pi I here. But however, we want to do a decentralized design. What does that mean? So if I'm at the load center, so this is my hometown, the city of Austin here, for example, even without knowing the network-wide information, even without the Texas grid operator telling me this is the network-wide failure locations. But if I'm observing the physical quantities for my own grid, for my own part of the grid, like the voltage, the line flow, and also the angle and the frequency, more importantly, if I can observe these local quantities, can I use a neural network to predict what should be the local load shedding, the LMP sensitivities? Okay, so this is one idea that we tested out for the real system. It works out pretty well, which it was surprising. With a local only measurements, this can be done. But then there is certain, this is the, although these policies, load shedding policies, are implemented locally, it does not mean that we don't need any centralized or global intelligence. Specifically to train these local policies, we need to do the training in the global location, knowing what is the impact of potential contingency on the grid in terms of how the measurement would change in response to this contingency, and then solving a centralized problem to know what is the best LMP or the load shedding decisions, and use that centralized information for the training. So basically the idea here is that although the implementation of these policies are totally decentralized or based on local data, but then these training process are fully centralized. And then through the centralized solution of the measurements or the optimal decision, we can train the scalable policy that is only based on local data. So I just want to highlight here that actually there is a high variability on these LMPs. So they are not that easy to identify with just local data. So this is a system with 14 nodes. So there is quite a range of the LMP value. For larger systems, there can be even larger variability as well. But then for the small system, which is the more recent results that we got, we see that if we consider multiple contingency scenarios, and then if the centralized training already know these scenarios that could potentially happen, and then train them on the local policy to predict the local LMP, the error is pretty small, so it is actually around 0.3.5 out of a 40 value. So the LMP here is $1 per megawatt hour, so which is the price of electricity, and then the average error percentage can be as low as 0.1% for all these prediction tasks. So this is something we're still working on now, and especially we're interested why the local information itself will be able to provide sufficient insight into how much the global situation is. And then our hypothesis here, which is we're trying to verify, is that the local measurements, although it's only in a certain nodes, it can effectively tell what is the contingencies impact, what is the impact of the land failures on the local systems. So it can quickly adapt to that contingency scenario to identify these failures. So with that, I want to sum up my talk. So I think the first part is on learning for the normal operations, the ACOPF, where we have seen that using the GNN topology, well designed, can simplify the model structure, and also interestingly making it very adaptive to any topology contingency or new topology for this topology transfer capability. And the second part is what we are still designing, is trying to do the scalable learning so that during emergency operations, just by using some localized information, we are able to understand what is the global contingency and be able to react effectively to this global contingency. So the mitigation is much faster, and then we can more promptly to mitigate the impact of this emergency situation. So on the first part, we're still looking into exploring how to use this graph learning or the GNN for static and most importantly, some also dynamic grade behaviors. So this is something has become interesting recently on using GNN for dynamic modeling as well. On the second part, we're trying to provide more analytical understanding on why the limited local information could give us some global intelligence or global policy, globally optimal decision as well. So this is something we want to better understand analytically. So with that, I want to conclude talk, and then this is where we have seen that the interest of using graph learning for power systems in a variety of work, and I think there are definitely more applications or more potentials of using these ideas for problems in power systems, and these are the references associated with the literature review in the previous slide. And with that, I would like to conclude talk, and thank you all for your time.
Thank you, Hao. Very interesting.
Thank you.
Okay, let's go to the questions part. So actually, my computer was out for a minute or so, so I don't see the previous chat anymore. But I think Mihir had some questions. So Mihir, you can unmute yourself if you want.
Yeah.
Yeah, actually, I want to ask if there are any published works on these two problem areas which could help me to further understand, because even my work is also related to graph learning, but the application area is slightly different. It's not on optimal power flow. So can I have any of these like any papers on regarding this which could help me understand further on how graph neural networks are being implemented, like in general? That is one question.
Yeah, absolutely. So this the papers that I mentioned. So this is the UPenn paper, and this is our recent paper on the GNN for ACOPF. I can share the slides or whatever to put these links to you.
Yeah, and the video will be online, so then you can check the references here. Okay.
And
Yeah.
I have another question as well, which is on the optimal power flow problem. So there the slide talks about filters. So I actually want to ask you, are they is it based on any graph shift operator? Like making it as a polynomial and then designing a filter out of it? Like, is there any method for that? Like in the first problem?
Yeah, a good point. So in the graph filter, we think it's a train of a parameter. So we could have used like a graph Laplacian matrix or like a adjacency matrix, but then we just set it up so that the sparse structure is similar to these matrices, but then the exact parameter values are trainable. So they are fixed by the training process. Yeah.
So the W is like the graph shift operator, right? What people
Right.
normally would fix. So it's an order one, you could say, right? So it's a polynomial of order one.
Oh yeah, we didn't use polynomial form, so it's directly the sparse structure as the actual Laplacian matrix.
And the HL
Yeah.
would be the filter coefficients then, right? What we would call, right? The HL, right?
Yeah, so L is actually the layer index. Sorry for the confusion here. Yeah.
The H matrix is like the filter. These are like the filter coefficients, right? To go from one feature input to another feature output, right?
That's right. Yeah. So this is to manipulate the rows, each nodal features. So you can do high dimensional mapping. Yeah.
So here you will learn both W and H then, I guess.
Yes. Mm-hmm. That's right.
Yeah. Because normally we only learn H, right? So in GNNs, I mean, sometimes, yeah. I mean, in the standard GNN, let's say, and the W would be kind of fixed.
Yeah, that's true. So we found out that actually, yeah, the learning W can also be done from back propagation or the gradient updates. Yeah, it allows for more flexibility to, for example, in the problem that we mentioned, the only a few like the nodal the edge quantities would affect the nodal quantities. So we believe that changing that can allowing that flexibility to train W can help us to identify this underlying dependency better. Yeah. Thanks for that clarification. Yeah.
Sorry, Mihir, for jumping onto your question, but it was also not.
Yeah, that's fine. I mean.
Okay, so also Pierrick has a question about the emergency response, whether the problem can be framed as a reinforcement learning problem, where an agent would try to mitigate failures.
Yeah, that's very good insight. Actually, there was a paper. I didn't show the exact reference. There was a paper to set up this problem as reinforcement learning, so that like you can implement the action and observe what action, how the action impact to the grade, and then use that interactive process to find the best policy. So we didn't set up this way, because what we are trying to do is try to mitigate immediate impact. So we're focused on the stage that we want to mitigate what's the immediate impact of the system. So we only set up in like the first stage, like optimization setup, that static optimization setup that only considers, okay, how immediate change can potentially restore the power balance here. Yeah. But that's a good point that people have been trying to use a reinforcement learning framework to do it. So if in the reinforcement learning case, that would be multi-agent reinforcement learning, so which might be very challenging to solve, or more challenging than single agent, I believe. Yeah. Okay. And I think there was a, sorry.
No, go ahead.
There was another question earlier.
There was another question from Jean, I think so, but I think the message got lost in his computers.
Yeah, you can.
I mean, actually, I had one question. Like, I mean, in the
Sure.
optimal power flow problem, the graph learning, is it like formulated as a convex optimization problem? Like, I mean,
Yeah, so the AC OPF is non-convex because of the quadratic power flow relation. If we linearize that, then we can come up with a convex version, which is called the DC power flow. So this is the convex version here. But then generally, people are more interested in the AC one here, which is a non-convex problem. Yeah, good point. Yeah, sorry, I wasn't able to change the chat pad. What was Jing's question again?
I think he was asking for like how many samples do we like, whether we need to sample many topologies while we training the GNN. That was
Yeah.
Thank you for the talk, Professor Zhu. Yeah, my question is, do we need to like sample many topologies during the training phase, or we just train on one topology and doing something like transfer learning during the prediction phase?
Yeah, good point. So actually, for typical operations, we have a good understanding of the topology. So it's only trained for a single topology, the input-output relation, meaning that the AC OPF is only formulated for a single topology. So there is some recent work which I actually just came through this year, is from if you go to this link here, so Dr. Minhua Chen's group, they have been trying to look into how to do the training even under multiple topology. So which means that the training phase will have a lot of more samples or sample generation effort. But then they seem to show that even with typical fully nominal neural networks, it is possible to incorporate the topology in like multiple topology in the training phase as well. Yeah.
Okay, thank you.
Yeah, thanks for the question.
Okay, then there's also, a new question on how this W then is related to B and A.
Yeah.
Learn
Good
W.
point.
Can
Yeah.
To B or?
Right. So the W so far we see it's more like sharing the topology, the structure as the B matrix. The entries could be different or very different from the B matrix, because in one sense it's actually the B inverse matrix. So that has a little bit differences there. We were not able to identify like the exact pattern between the B and the trend W. So I want to point out that although like it is generally generated by the B inverse subspace, but then actually which where are the congestion locations still play a very important role in this prediction. So for example, in this sense, you can see this is only like you see like this is more like a clustering. So which means that the congestion usually is very, very few. So where these locational differences are activated, sometimes like sparser than the actual the B matrix can enable. So there is this kind of more like a specified relation because of in practice the active lines are very few. Yeah, but that's a good point. It's interesting if there are some good relation that we can explore here.
Yeah. Any other questions from the audience?
I have one more question.
Sure.
Can these two problems be formulated in terms of compressed sensing? Like, I just want to have a thought.
Yeah, a very interesting question. So I think because like essentially, can we try to infer like the price everywhere even if we only have just a few price location samples, right? That's I guess the idea. here, or the relation to compressed sensing, if I understand correctly. So I
like kind of a weighted least square type of problem, like which is regularized on L1 or L2 norms. Like, I mean.
Yeah, definitely. So I think so that's the main idea explored in at least two papers that I know. One is this paper by the UMN researcher, very interesting, that using the prior of the graph to better do state estimation when the observability is low, and then similarly here is to use GSP as well. But I believe very similar ideas that when the observability is low, meaning that we only have samples in a few locations, the graph can provide a natural prior for be able to exploit the observation in other unobserved locations. Yeah, very interesting comment. So
yeah, Jean, go ahead.
Hi, so I have one question about the transferring your GNN model for changing topologies. So you'd mentioned that you do use only half of the samples, which have to be regenerated, right?
that's true. Yeah, that's right.
The regeneration process, do you use like load flow analysis, or like do you use a typical traditional solver to obtain those samples?
Yeah, very good question. So so the regeneration, I think we tend to need to sample it around the new congestion location or the contingency location. So there are strategies that we took heuristically to do this regeneration, but then I want to point out that there was also, if you go to like the wiki page, there are some work that considers some adaptive sampling strategies, which we didn't get into in details. But then there are strategies that can like do the sample generation strategically by looking into what kind of samples can provide more like a feasibility like shaping understanding of the feasibility of this problem. So we didn't get into that. We did maybe more like a heuristic way to think about where the samples could differ from the original topology. Yeah.
Right. So does it support online learning then to generate 4,000 new samples using traditional approaches? I mean, we can sample it strategically, but we still need to solve the power flow problem, right? Am I right?
Yeah, we still need to solve the ACOPF. Yeah, that's true. Yeah, I think that's a great idea. Yeah, to think about the sampling, which plays an important role in this problem. Yeah.
Right. And half of the samples, was it like, is it just a number that, is it something that's you have tested empirically, or is it, is there like a theory behind it? I'm just curious.
Yeah, actually, yeah, good point. Yeah, so we picked that just to showcase that, yeah, it's a good number, but yeah, no theory so far. Yeah.
Okay, thank you so much.
Yeah, thanks for the question. Yeah, very insightful.
Other questions?
Oh,
Yeah.
Yes.
I really enjoyed your talk and obviously your research, and I pass on the greetings from the very warm summer-like weather, Minnesota. Right?
Yeah.
Two things that occurred to me as you were presenting. The first one relates to the decentralized operation based on local measurements. It seems to me that you could benefit from federated learning type of approaches. Have you thought about it? Also, at least in communicating measurements to the central unit. That's one thing. And the second would be that these people that talk about meta learning and transfer learning approaches precisely aim at settings where you don't have too many training data, and then you can accelerate from different topologies the learning process. So this could be two things that you could consider exploring, I guess.
Yeah, very good point. Yeah, so definitely, I think on the decentralized policies, yeah, we could have explored like in the training phase how to set up a centralized coordinator to more effectively coordinates between the decentralized agents and then to do the information sharing.
Yeah, and also some of the local collection measurements could be better than other locals, right? So which locals are the ones to rely upon, right? For example, intuitively is the one that have higher derivative in their cost function, right? They are basically
that's right.
estimating the global.
Yeah, we definitely could benefit a lot from setting up the problem with more like a global interest, or like the impact of the local measurements, global the benefit to the global decision making, and then have better strategies to deal with that. Yeah, this is definitely something we're lacking so far. Yeah, for the transfer learning part, it would be very interesting to hear your ideas too. Yeah.
I think that you're doing excellent. So we're proud to watch your research.
Thank you. Yeah,
That's
thank
why
you for
also
the support.
The official Minnesota background.
Yeah, looks everyone has a great weather, nice weather in the background. Yeah.
Reality might be different, but
yeah, that's great. The grid has no emergency. It's working perfectly today. Yeah. Excellent.
Thank you.
Thank you. Yeah.
Okay, if there are no more questions, any urgent question? If not, then I think we can wrap it up here. So thanks, Hao. Very nice for you to join online and to present this work. So
thank you very much for inviting me, and thanks everyone for coming today. Yeah, really appreciate that. Yeah,
thanks everyone, and see you next time.